Hello chemists and welcome back to this episode of Bale's Chemistry. We are looking at how to substitute ligands in transition metal complexes. This is 2.5 on the AQA A-level chemistry specification and it's going to appear on paper 1 of your final exams. So before we jump into this idea of substituting ligands, we're first just going to have a quick recap of Gibbs free energy. If you can't remember all the details, it might be worth going back and having a look at our thermodynamics playlist. The link is at the top of the screen now. The main highlights that we're interested in then is that Gibbs free energy delta G equals delta H minus T delta S. Now, what we need to remember from that is that when we have a negative delta G, we have a reaction which is feasible. One of the ways that we can have a more negative delta G is by increasing the delta S, or the change in entropy. We could also decrease the change in enthalpy. It's useful to bear these two factors in mind as we go through looking at the different ligand substitution reactions which can take place. So the first example we'll look at is when we swap the ligand for a ligand of a different size. The three monodentate ligands that we're most familiar with are water, ammonia and chlorine. If you remember, water and ammonia are a similar size and chlorine is much bigger. If this happens, we'll see a change in coordination number. The change in coordination number leads to a change in the shape. So most complexes with chlorine as a ligand are a tetrahedral shape, whereas most complexes with water or ammonia as a ligand are an octahedral shape. And because chlorine has a negative charge, we'll also see a change in the overall charge of the complex. If we look at this example of cobalt surrounded by 6 water ligands being replaced by 4 chlorine ligands, one of the biggest things we can see is the increase in number of molecules. We've gone from 5 molecules on the left-hand side to now having 7 molecules on the right-hand side. This causes an increase in entropy. This increase in entropy makes the cobalt chloride complex more stable than the cobalt and water complex. We can look at another situation where ligands are swapped for a ligand of a similar size. In this case, water and ammonia are very similar sized monodentate ligands. When this ligand substitution reaction takes place, there's very little change in the enthalpy or the entropy between the reactants and the products. This means that the substitution reactions are easily reversible, and neither the products or the reactants are particularly more stable than each other. However, the equilibrium between them can be influenced by the strength of the coordinate bond that they form between the metal ions. If we look at this example here, we've got cobalt with 6 water ligands being replaced by 6 ammonia ligands. Now we don't see that big change in entropy like we did when we swapped it for a chlorine ligand, but like we do for all ligand substitutions, we do see a change in colour. When we substitute a monodentate ligand for a bidentate ligand or a multidentate ligand, we have something called the chelate effect taking place. This results in a more stable complex being formed. This is due to a significant increase in the entropy, whilst the change in enthalpy remains very similar. This is because the energy of the bonds broken is very similar to the energy of the bonds formed. If we look at this example then where we take copper surrounded by 6 water ligands and replace that with 1 EDTA molecule, we can see we've gone from 2 molecules on the left hand side to 7 molecules on the right hand side. This is a significant increase in entropy. What does happen in this process is we change the charge on the overall complex. Both these shapes are octahedral as they both have 6 coordinate bonds. There's a much more stable complex formed on the right hand side with the copper in the EDTA because of that massive increase in entropy. Thanks for watching this episode of Bale's Chemistry today. I hope you found it useful. There's quite a few complicated concepts at play here, certainly when we talk about the chelate effect and increasing the level of entropy during the chemical reaction. If you've enjoyed it, hit the thumbs up below, and if you've got a bit of time, why don't you go back and watch our thermodynamics playlist all about Gibbs energy and entropy changes, or go back and revisit the transition metals playlist.